Hello, atmospheric science students. Here I am, Dr. Shruggy, trying to show you how to do Monte Carlo integration for some relatively small samples. N is only equal to 10,000 on here because we're just doing this in an Excel spreadsheet. We don't want to go nuts and try to have billions of lines or something like that. Whereas, of course, in a software program, a model or something, you could just have this in a loop and do it far more times than this. Let me just give you a quick example here. The problem that we're trying to solve in this first example, which is available to you, it's called First Monte Carlo Integration Example for ATS 570, and it is available to you on Blue Line. It's the integral from 5 to 10 of x squared dx. We're going to use a Monte Carlo integration with a simulation of n equals 10,000. And I'm going to zoom in a little bit here just to make this a little bit easier for you to see what's all going on. All right. So we have to set the values of the limits of the integration, a and b, which will be equal to 5 and 10 respectively. And we need to know that those are the limits in the x direction. And then in the y direction, our rectangle that we're circumscribing around our integration extends from y equals 0 to y equals some maximum of this function. Now on the region from 5 to 10, the largest value that y can achieve is 100 because the of f of x or whatever could achieve is 100 because x squared is what you're integrating over, and it goes up to 10, so 10 squared is 100. Let me show you in just a minute or two a graph that illustrates this a little better. In fact, I'll go ahead and do that right now. You'll see more about what this graph is in just a minute, but for right now, the solid black line here is the curve that we're integrating. We're trying to find this area under here, and you can see that the x-axis extends of this kind of pinkish area that I've got colored in here is the rectangle that we're using as sort of our dartboard, if you will, for Monte Carlo methods, and it extends from x equals 5 to x equals 10, and from y equals 0 up to the maximum of the function in that range, which is y equals 100. So this is the rectangle that we circumscribed around our region that we are integrating. All right, now I give you in this spreadsheet here two columns of random numbers. There's 10,000 random numbers in these columns here, and if you remember from the pen casts, I called them R1 and R2. You have a total then of 20,000 random numbers, or 10,000 ordered pairs of random numbers. They are uniform random numbers, meaning that they are evenly distributed between the numbers 0 and 1. And so we just need to map those onto like the random locations that we are picking inside of our rectangle, x and y. Now remember, we talked about how to do this in the pen cast here. X, if you look at the equation up here, the equation bar is, the formula bar, is x is equal to a plus b minus a times the value of R1, which is in cell A20. Now notice I used, I defined some names in here. I defined this cell right here in cell B10. I defined that as being cell A, and I defined this cell B11 as being B. You can see that up here in this name box. And I defined this cell B14 as being max. Remember, you can do this for whatever you want. I mean, if you want to call this, I don't know, score for lack of anything better, and you got a 100% over here, then you just, once you've selected the cell that you mean to name, you just go over here and wipe out its name and change it to whatever you want it to be. Now this cell is called score, and if over here I want to say equals score, it'll just copy that. All right, so over here in column X, these are the random locations on the x-axis, 10,000 of them. Y is the same sort of thing. It's just, if you remember how to change R2 into Y, it was just the maximum times R2, so it's max times cell B20 here. I copied those down 10,000 times, all right? Now, Monte Carlo integration is pretty simple. Hey, by the way, let me show you what that is. I'm going to go back over here to this other tab. That is what this pink area here is. Every one of these little pink spots here is one of my 10,000 spots. Those are the 10,000 randomly chosen locations on this plot. Some of them are above the curve and some of them are below the curve. The fraction of them that are below the curve is in some way an estimate of the area under the curve. So let's figure out what we're going to do with that. For every one of these random values on the x-axis, we now compute f of x. F of x is very simple. It's just x squared. So for this value of x, f of x is just x squared. Copy that down 10,000 times. No problem. Now the question is this randomly chosen value of y above or below the curve of f of x? That's just going to be an if statement in Excel. We talked a little bit about those in the pen casts, and I have it right here. If you look up here at the formula bar, if the value in E20 is less than the value over here in G20, put a 1 in this column. Otherwise, put a 0. So like in this first one, because the value of y is actually above the curve, we get a 0. And the next one we get a 0, and we get a 0. But then here comes a 1 right here, for example, where 17 is less than 33, so we got a 1 right here. Okay, copy that down 10,000 times. All right, then I just made myself some little results over here. My little n is the sum of all those 1s and 0s. It's how many times we ended up with a point that was below the curve. Big N, I just typed in the number 10,000 there. That's how many samples, how many random points we chose. A, if you remember, was the area of our rectangle. It's 5 units wide and 100 units tall, so it has an area of 500. So our estimate, which is little n over big N times A, our estimate of this integral is 292.25. For what it's worth, the correct answer, according to just doing math, it's just a simple power rule integration, is 291.67. Our estimate is not really all that far off. Now, of course, it would depend on what you're doing with this data. But as an estimate, that's not terrible. And that was only n equals 10,000. Feel free to use n equals 10 million if you weren't doing this on an Excel spreadsheet. On a spreadsheet, it might get to be a bit cumbersome. But in a C program or something, you would just increase the number of times it goes through the loop. No big deal at all. So we got a pretty good estimate of that integral just using 10,000 samples. Let me show you another one that actually shows a better example of the kind of thing we would be doing with Monte Carlo integration. This Monte Carlo integration right here is for this function from 0 to 4 pi of the sine of x cubed times the sine of x squared times the sine of x plus 1 dx. That doesn't look so horrible until you look at the graph right over there. That's what the graph of that function looks like. Oh my goodness. That is not a well-behaved function. The farther you get down the x-axis, the faster the oscillations get. There's no way you could define little trapezoids that would have any meaningful representation of the area under that curve. They would, no matter how narrow you made your trapezoids, as you got farther down the x-axis, every trapezoid would be spanning many maxima and minima of the function. It would just not ever converge towards a solution. The error term would be very large. But Monte Carlo methods don't have that problem at all, and we're going to see that we're going to get a darn good estimate of this integral. All right, so let me again switch over here. I'm going to zoom in to a double magnification just to make it a little easier to see what's going on. All right, here I made again an area of my spreadsheet where I put the limits of the integration from 0 to 4 pi. And again, as you can see with the name box up here, I actually defined these regions. The maximum of this function over that region, where do I have that? You can see it can't get higher than 2. So I made my maximum of my function over that region 2. Then I have those 10,000 R1s and R2s. They're the same ones I used last time. All right, and I mapped them to values of x and y using those functions. A equals b minus a times R1, and y is equal to max times b20, R2. And if we actually go back, I have a little, again, you have this spreadsheet available to you on Blue Line. This is actually what that function looks like with the 10,000 randomly chosen spots painted on top of it. And just to show you why this is a real problem, remember we want to have these little spots, we want to see how many of them are below this curve here. You know, look how as we get farther and farther to the right here, if we choose little areas of this curve, okay, this curve here is going up and down very, very fast. It's oscillating so fast we're not even getting good plots of it in Excel. If I just go over here and I format my axis and show it a narrower range here, like if I only show you the region from, like, let's just say 10.2 to 10.3, just a little area here, that tiny little wiggles that were in there, now we can see as we zoom in very close, well, some of the points are below that and some of the points are above it. What was just a tiny little wiggle we can hardly even see on the original is still got points inside of it and above it and below it. That would be very hard to do with a midpoint rule or a trapezoid rule, because these little wiggles are getting very, very, very small. Every rectangle we draw spans lots of maxima and minima. We're not going to get a very good estimate here of this integral. Monte Carlo methods don't care about that at all. They're not going to have any problem with this not being a well-behaved function. So in this case, for example, now that we have the values of x and y for 10,000 locations on our plot, for each of them we can compute f of xy. So for this value of x over here in cell D20, I have the sine of x cubed times the sine of x squared plus this, times the sine of x plus 1. That's what this little function here is. And then we just have to test, is our value of our randomly chosen location of y below f of x? That's just a little if statement again. If that cell is less than this cell, put a 1 in there, otherwise put a 0. All right, I didn't realize this graphic kind of covered this up. Let me move this out of the way here. So, where did I do that here? Okay, so I summed up all the values of those 1s and 0s. That's going to give me little n, the number of points that are below the curve. Big N was 10,000. That was the number of points we drew. The area under that, in that rectangle was 4 pi times 2. The width of the rectangle was 4 pi. The height was 2. It's 25.13. All right. The estimate of our integral using the Monte Carlo method then is little n over big N times big A, which is 12.94. I can't imagine how it does it, but Wolfram Alpha actually does know the true answer of that integral. Can't believe that there's actually a solution for it, but there is, and the right answer is 12.8636. Well, look, our integral is actually, well within 1% of our estimate of the integral is well within 1%. I mean, this was actually not a terrible method at all. I didn't go through and actually compute this using like midpoint methods or trapezoid rules or something, but there's no way they would converge to an answer that close with just a few rectangles or whatever. This is actually really a very efficient way to solve the problem. And that was just 10,000 points. We could just as easily have chosen 10 million if this wasn't in an Excel spreadsheet. All right, so you can mess around. You got these two spreadsheets available to you. You're going to go ahead and just cut and paste these 10,000 values of R1 and R2 into your spreadsheets in order to compute your estimates of the Monte Carlo integration. But we will do that. I mean, I'll leave that for you to do later. And please let me know if you have any questions. This has been Dr. John Schrage.